Angla is what?
Sí, puede pasar por aquí. Sí,
Đúng rồi, phải lúc sai đâu. Đúng rồi. Làm đâu còn sai. Làm đâu còn sai đấy.
Alright guys, see you.
Làm đâu còn sai.
I just need a banner that says I gotta fly into this room. Well, anyway, I was trying to tell you yesterday that the renormalization group is a trick you can use for two kinds of problems. One is to understand universal behavior in critical phenomena. Other is when you ask the following question. I have some Hamiltonian H0, which I understand, and I want to add to it some extra term, and I want to know if that term makes a difference or not. Now I said, of course, every term makes a difference if it's non-zero. So the question you're asking really is, if I'm interested in very, very low energy physics, does it make a difference whether I add this term or not? Because it's quite possible that in a big Hilbert space where all the states are kept, this parameter has a value, 0.1. But if you find the theory that affects just the low energy sector by integrating out the high energy sector, this parameter may be much bigger or much smaller. If it's much bigger, well, you have to pay attention to that. If it's much smaller, you can ignore it. That's the goal. More importantly, suppose there's a rival theory that says maybe that interaction is what we should look at. They will make estimates and they'll tell you from the lattice and whatnot, this number is bigger than this number. But that's not what you should go by. For your particular question, those initial numbers are not relevant. In the effective theory at very low energies, it's quite possible that the relative importance of these can change. So how are we going to use the RG to find that? I will do a concrete problem that's going to be much more useful than vague generalities. The concrete problem is a lot of fermions living in one dimension. They've got no spin. They live at a site labeled n. And the Hamiltonian, or the non-interacting problem, is this minus t psi dagger n plus 1 psi n plus Hermitian conjugate. So this is just fermions hopping on the lattice. So we know what to do with this problem. We make a Fourier transform from psi n to psi k. You do that, you stick this in, and you know what you will get. You'll get minus 2t sum over the momenta k, psi dagger k, psi k, cos k. So you draw the picture here. It looks like this. The zone goes from minus pi to pi, and this is pi over 2, and that's minus pi over 2, and all these states are occupied because in those states the energy is negative. There, you solve this problem. The ground state is the occupied region, and you know all about this thing. The most important property is a system with no gap, meaning I can agitate the system with no appreciable input of energy. And you know what that excitation is. You take a guy from just below the Fermi surface and put it just above the Fermi surface. And the energy cost will be just the difference of this energy and that energy. And you created what's called a particle-hole pair. A system which can be excited with arbitrarily low energy will have a DC conductivity. because for DC conductivity you apply a frequency omega, which can induce the transition by energy h bar omega, then you let omega go to 0, this guy will conduct. So you know the main properties of the system. Then the question is, let's call this Hamiltonian H naught, but now I want to add an interaction. Let's add the following interaction. So the Hamiltonian I have is this H naught, plus I want to add some repulsion between these fermions. Now, since these are spinless fermions, there's no way they will come on the same side. So the next best thing is you have a charge density at site n plus 1 times charge density at site n. You want to add that repulsion. So two fermions which are in neighboring sites will feel a repulsion. If they're 2 units away, they don't feel each other. So this is some kind of caricature of the Coulomb interaction. But it's too short range. But this is the question I want to ask. I want to ask myself, if I turn on this non-zero U, what will the system do? Well, I can understand some extremes of this. One extreme is U equal to 0. When I convinced you it's a metal, meaning it's got conductivity. The other extreme is when U is very, very large. Now it's very, very large. Let's focus on this term. First, you got to realize that since you got half the states full and half the states empty, this is called a problem of half filling. You got half the number of electrons that you could possibly have on this lattice. Remember, they have no spin. But every side you can only put 1 electron. So you got n sites and n over 2 electrons. And U is very, very large. So what this U is telling you is every electron says, I don't want a neighbor. If I have a neighbor, I have an energy cost. So that's one way to take care of that, which is to take your lattice, put an electron there, leave the next side empty, an electron there, leave the next side empty, and so on. So that's the charge density way. And notice that nobody has a neighbor, so this U term doesn't get to do anything. But the minute you try to do anything to this ground state, the minute you move anybody here or there, you immediately up against a big energy cost, because the minute this guy moves, that's the nearest neighbor. So you cannot move this guy around from its ground state without paying a price U. So that's a system with a gap. So there you should imagine in your mind a ground state and a gap size U. This system is an insulator. So for not only infinite U, but for very large U, you can see it's an insulator. And for very small U, you might think that you can maybe perturb this metal and maybe there's a metallic region. Suppose the question is, when does it change from insulator from metal to insulator? Maybe it happens right away, or maybe it happens with some strong coupling. That's the question we're asking. Now, if you ask some people what this system would do, they do what's called mean field theory. So mean field theory is where you offer the system some attractive ground state and say, are you interested? For example, you may offer a ground state in which the charge density at any given site has some average value, which was what, 1/2 in our problem, and it alternates like this. That means half is average, then it's more or less, more or less, more or less. It's alternating charge density. And you say, if I assume the density has this part, plus some quantum fluctuations, you can take an assumed form, put it in the Hamiltonian. And just like yesterday you saw dynamical mean field theory, this is a very simple mean field theory, and you see, can I get a state of lower energy? You will find yes. The system will immediately accept this option for any U, however small, because its susceptibility to such a perturbation is infinite, and divergent, logarithmic divergent, so you'll definitely go for it, and you will find for the smallest value of U, you'll get a mean field solution in which there is charge density order. So you might say, okay, that's what it does. Case closed. But another person can say, I believe the system would like to have superconducting order. You offer the system some average psi to be not zero, you will find that also has infinite susceptibility, and you can argue then that's what it will do. So all these different mean field factions can claim victory because each one will have a solution that's better than this free Fermi sea. So the question is, what really happens? Now, that's why I like to use the renormalization group in this context. The renormalization group, I will show you, is an unbiased way to decide what it will do. It doesn't care whether you prefer this or that mean field theory. It will tell you, it's an automatic machine, to tell you what is really important at very low energies. And we are talking about very low energies because we're talking about the nature of the ground state. We're not interested in 27 million MeV over this ground state. We just want to know what's the ground state doing. So the RG will show us, in a way I'm going to explain to you, what the system really likes to do. So what's the strategy for using RG? The strategy will be the following. We will first take just H0. Forget lambda. Take that theory, write a partition function for that. So that will look like some integral over permions, which I will schematically write like this, with some action. I will tell you what the action is, but let's say that's what you do. I will find that I can do a mode elimination in this theory so that S0 goes into S0. And the S0 is the fixed point of my renormalization group. So what I'm telling you is I'll take the non-interacting theory, I will eliminate some variables, and the action, or whatever, will come back to exactly the same form. There is no flow. Then I will add the H1. Then the action will look like e to the S0 plus lambda times the extra term. Now I will eliminate variables the same way I did before. Then I will ask, is this lambda getting bigger or smaller? If lambda gets smaller and smaller, I say it's irrelevant, forget about it, this interaction doesn't matter. That means at least for weak values of the interaction, we'll go back to looking like a method. Or maybe this lambda will keep growing. That's an indication. I mean, I shouldn't have called it lambda, right? I'm sorry. This is what I call U in this problem. I'll find U keeps growing, then maybe it's going toward this side, in which case it's going to be an insulator. That's the strategy I'm going to use. You will find out along the way that this way of doing it leaves it open for all possible instabilities. If there's instability you never thought about, suppose you never heard about BCS instability, and it's bound to happen. If it's going to happen, the RG will tell you. Because a certain coupling constant, which you didn't even think about, will emerge and start growing and say, look at me, look at me. That's what you will do. So you don't have to have any intuition, which is why I like this machinery, because in condensed matter, my feeling for what systems to do is fairly limited, because the subject is so rich in phenomenology. This machinery will tell you what to do. It will even give you ideas if you didn't have them. And my goal is to show you that all the instabilities we talked about will all come out of this machine when I apply it in 2 and 3 dimensions, 1 and 2 dimensions. All right, so let's see what I should take for my theory of the S0. So the Hamiltonian H0, remember, it looks like minus 2t sum over momentum k, psi dagger k, psi k, cosine k. So I drew the picture, I'm going to do it again. All these states are filled. And this is my Fermi momentum, this is minus kf. The first question is, what do you think is the low energy region for this theory? Most people think low energy means low momentum. That's certainly true if you got a single fermion. The lowest energy may be lowest momentum. But for a many-body problem, low energy means if I hit this guy on the head, the hammer, what's the thing it's going to do? Who's going to get excited? Well, electrons down here, they cannot do very much, because they cannot go anywhere. They're trapped by the Pauli principle. Only the electrons near the Fermi surface can do something. In other words, even if I artificially kept these fermions from moving from those states, it won't make any difference because they won't have moved anyway. The only fermions that can respond to anything I do are the fermions near the Fermi edge. So low and high energy in this context really means momenta near and far from the Fermi momentum. So what I'm going to do first of all is I'm going to create an artificial theory in which only these states exist. They have a width minus lambda to plus lambda around either Fermi point. So that's a theory with a cutoff. And the hope is, in the end, the fact that I threw out the bottom of this band will not make any difference. And you can see why. For weak perturbations and weak interactions, whatever perturbation you do, the bottom of the band is not going to get involved. Only the guys near the Fermi energy will get involved. So I'm going to truncate this theory, and if you blow up this region here, you have to trust my drawing here, it looks like the energy versus momentum is a straight line with positive slope. For the momentum, I'm talking about little k is really k minus kf. Likewise here, there's a region where the slope is negative. That means if you change k minus kf, the slope is negative. So if I write this and you guys tell me if you believe this or not, that is one set of fermions and there's another set of fermions. We call this right, psi dagger left, k, psi left k, bf k. This little k, I'm sorry, this sum I'm going to replace by an integral of little k from minus lambda to lambda, and this one is also integral dk from minus lambda to lambda. Near the right Fermi point, if I increase little k, the energy goes up. That slope is what I'm calling Fermi velocity. Near the left Fermi point, if I increase k, the energy goes down. That's why this comes out with a minus sign. All right. And I've kept the theory in a bandwidth minus lambda to lambda. So df, which is the slope at the point, I'm going to choose to 1 for convenience because it won't change anything. This is one of the interesting cases where you start with non-relativistic fermions, but the physics look like relativistic. If you look at the Dirac theory in one dimension, you know the Hamiltonian for Dirac fermions is what? Psi dagger alpha dot b times psi, but alpha you can choose to be this matrix. So you get linear dispersion relation even though without any Fermi C it's quadratic. And similar things happen even in 2 dimensions. You take a material like graphite, graphene, you will find that there are relativistic fermions. This is one example. Alright, so we're not interested in the relativistic part, but you have to know, everybody understands why this is the starting point for my theory. But very large values of little k, deep down here I'm making a mistake because it's not going to be linear, there are some quadratic corrections and so on. I'm saying, forget that. So what is the path integral for this problem? You remember my telling you yesterday that if your Hamiltonian looks like b dagger b times omega naught, then the partition function for that guy is d psi bar d psi at different omegas times e to the psi bar omega I omega minus omega naught psi of omega b omega integral. Well, that's exactly what I have. Every one of these guys is a Fermi oscillator. This is like the B of that problem. But that is 1 for every value of little k. And the energy of the oscillator is just the number little k. This is a Hamiltonian that you have. And the partition function then in this problem will look like I'm going to use a compact notation that hides the fact that the psi, there's a psi for every k and for every omega. Omega comes because when you do the time slices, there's a psi for every time. When you do Fourier transform, there's a psi for every omega. You had that even with one oscillator. Now we got an oscillator at every value of k. So what will be the action? Action will be integral psi bar omega and k I omega minus, I will tell you what this little symbol is. Psi alpha omega and k d omega dk over 2 pi squared. So maybe you can guess what the extra index alpha is. Alpha is an index that can be called either left or right. And if it's right, epsilon is positive. If it's left, epsilon is negative. That just takes into account the fact that the slopes are opposite at the 2 points. So you took a single non-relativistic fermion and traded it for 2 relativistic fermions, one with E equal to k, other with E equal to minus k. And the partition function is then just union of all these oscillators. So now I should write the limits here. Limits are very important. If you look at the limits here, omega goes from minus infinity to plus infinity, and k goes from minus lambda to plus lambda. You realize it's a Gaussian theory. It's a Gaussian theory because omega and epsilon are all numbers. I have a quadratic function, psi bar sine exponential. It's a Gaussian integral. You can do everything, you know all the averages. So what I want to do is to change my cutoff. So remember what I had. I had kf, and I had a width here, minus lambda to lambda, and at minus kf, I had minus lambda to lambda. I'm going to go to even lower energies. Already the linearization is low energy physics, but I want to go to even lower energies. That means I want to eliminate some states so that the new bandwidth is even smaller. I want to go to lambda over s to minus lambda over s. I want to change my cutoff from lambda to lambda over s, but s is some number like 2. S is bigger than 1. So I want to banish from this theory all the single particle states whose energy lies between lambda over s and lambda. I want to integrate them out. So when I'm finished, all I will have left are psi's labeled by k, the new bandwidth, with all possible omegas. So how do you do the integral? You remember this integral, the d psi, is a compact label. It means there are psi bars and psi's whose k is bigger than lambda over s, and there are psi bars and psi's whose k's are less than lambda over s. So I just want to integrate out the ones I don't like. You notice that this integral factorizes over all the different k values, because the integral, if you like, is an integral. The action is a sum over different k values. And if you integrate them independently, the Gaussians you don't like, you can integrate them out. Suppose you do that, what will you get? Well, do the integral. The ones you don't like would have been integrated. They will give you some number, but in the world of partition functions, a constant number, multiplying it doesn't make any difference. Because you're going to divide by z every time you take an average, which there at the top and bottom. We don't care. So the remaining theory looks like this. Let me just follow the action. The action now goes into the following: minus lambda over s to plus lambda over s, d omega minus infinity to infinity, psi bar alpha, omega and k, I omega minus epsilon alpha k, psi omega and k. And this sum over left and right. Look, it's pretty simple in the sense that what is left looks like the old theory with a new cutoff, because the ones you don't like have been eliminated with no effect on these guys. because they don't talk to each other. Now, is this a fixed point? It's not a fixed point. It's a Gaussian theory, but I don't like the fact that the cutoff is now different. Cutoff used to be lambda. So what I do is I introduce a new momentum k prime, which is s times k, and a new frequency omega prime with s times omega. What happens when I do that? Well, maybe I should write it here then, the result of doing that.
What is the motivation for rescaling omega?
Okay, I'll explain to you. What you want to do when you do renormalization is if you got a part like S0 and an S1 you're planning to add, right? You want to eliminate variables and you want to see if the interactions become more or less important. Now, how do we decide if something is more or less important? Just because the number u becomes smaller doesn't mean it's less important, because the non-interacting part may have also changed. So you want to keep the non-interacting part exactly the same in every respect. Then, if the interaction now looks bigger, it really is bigger. If smaller, really is smaller. That's the purpose for keeping the Hamiltonian, the free part, fixed. So even if you don't scale it, it is still a valid representation of the theory with a change cutoff. But you cannot tell at a glance whether the coupling has become more or less important. So we want to make after all, if the cutoff looks different now, who knows when you do the perturbation diagrams with a new cutoff, maybe the interaction will be bigger than the coupling constant such as. So you want to leave no room for doubt. So what you do then is you do what I said. You introduce a k prime, which is s times k, omega prime is s times omega. Then the action becomes d omega prime over s. Limit of omega is still minus plus infinity. dk prime over s, which is now exactly the way I like it. But there are all these 1 over s's. I'm aware of that. And then your psi bar, omega is omega prime over s. This is k prime over s. I omega prime over s. Minus k prime over s. Psi of omega prime over s. K prime over s. There is an index alpha I keep forgetting because it's really not doing anything very sexy, but I may forget and bring it back. It's coming along to the right. Yes?
The fact that the frequency scales the same way as momentum is because of the linear dispersion relation. Otherwise, you would have to use a different dynamic exponent.
That's correct. It starts out this way. If this had been omega squared or something. See, what I'm trying to do in the end is to pull out the same power of s from both these terms. Otherwise, what will happen is if you have different powers of s, one of them will definitely just vanish or grow relative to the other one. So it's possible in this theory to have them maintain the same importance. I want to keep both these terms equally important. Turns out it's possible, but like you said, with different dispersion relation, you may have to scale omega differently. That's a very useful thing to know. If by as in some problem, this was say k squared, then this will become k prime squared over s squared. This will become omega over s. Then you can see for very large s, you can just forget about this. So that won't be a fixed point. But I'm saying here, it's possible to keep this fixed. So let's see what we've got. I've got my limits the same. I got a 1 over s and a 1 over s and a 1 over s from here. So let me divide that among these two Fermi fields and put an s to the 3 over 2 here. Drop on this and s to the 3 over 2 here. So let me call this new thing here as a new variable, psi prime of omega prime k prime. I will define to be the old side of omega prime over s, k prime over s, divided by s to the 3 over 2. So look what I do. I rescale frequency. I eliminate momentum. I rescale the momentum. And I also rescale the field. So that the new field at omega prime k prime is the old field at omega prime over s and k prime over s. It'll all work out because if you pick a k prime between 0 and lambda, you will need the old field at a momentum between lambda over s minus lambda over s, because this range will be that, and there is always a field in that range of momentum. So you blow up the region, but you can map every point of the new bandwidth to a point on gold bandwidth. So if you do this change, what do I have now? You can see I am now deliriously happy. Everything is just the way I like it. This is called my new field. I'm not going to write that down. You can drop the primes. Right, let's drop the primes now. The action has come back to where it is. Maybe we'll keep it for a while. You'll see why it's important. So it takes all this work just to do the non-interacting. Yes?
If you have a narrow energy range, then you're going to have the same problem with omega.
Why?
Because your limits will now change as soon as you do this.
You got to be careful on what the energy really means. The real energy is measured by this number k. The omega is to introduce a time dependence of the problem. You should not equate this omega to real energy. To convince you of that, go back to the single harmonic oscillator. The energy of this oscillator is omega naught, right?
Okay.
And yet you've got this omega that goes from minus to plus infinity. It's not a real measure of the energy of the oscillator. So the analog of omega naught is little k in this problem. Also, Claudia brought up this point last time. If you limit the range of omega here, you can do that. You can also eliminate some high omegas. But unless all omegas are present, I cannot replace I omega prime by dt. And that's what you really need to get a Hamiltonian. So you cannot maintain a Hamiltonian picture if you limit the range of omega. So I prefer to keep all the omegas, but cut down the k values. Yes?
To add to her question, the omega is not the energy, but the pole. You think about that as a pole?
Yeah, I agree. It prefers to be the low energy physics will have omega near omega naught in the propagators. That's correct. Okay, so I have now found a mechanism by which S naught goes into S naught. That's all I wanted to say. All this work is needed just to get the non-interacting theory to be a fixed point. But now we can add the interaction. So I want to consider now the action S, which is the S naught I wrote down. I'm too lazy to write it over and over. But let me add an interaction. It's going to be the following. Remember, in the lattice I had an interaction, psi dagger psi at n times psi dagger psi at n plus 1. You can ask, if I add an interaction, is it going to grow or not? But I'm going to do something far more ambitious. I'm going to add the most general interaction involving 4 Fermi fields that you can think of. So my little guy is part of that general question. Because if I settle that question, you might come with a new interaction and say, what about that? So I'm going to add, this is the mother of all interactions. I'm going to put an interaction that covers every possibility. And it looks like this. I will tell you what this notation means. U has a subscript, alpha, beta, gamma, and delta, and I get d omega 1 up to d omega 3, dk 1 up to dk 3. So what is this? What is 4? 4 is a shorthand for omega 4 and k4. So I'm just tired of writing the energy, momentum, frequency, and momentum labels. And U is a function in general of all the frequencies and all the momentum. And also on this discrete index that tells you whether psi is from the left or from the right. This is the most general one. If you go back and take psi dagger n plus 1, psi n plus 1 times psi dagger n psi n and did the Fourier transform, you will find it looks like the same interaction with a particular form for U. But I'm not interested in that one interaction. I'm interested in adding the most general interaction.
The
So-
integration variables run to omega 4 or omega 3?
Why is it going up to 3? Is that you have energy and frequency and momentum conservation. So that's why there will be 3 of these guys and 3 of those guys. If I know these 3, I can figure out the 4th omega and the 4th K. You have to be a little careful. What's really conserved is the big momentum, not the momentum measured from Kf. But you will find in all these problems, if you write the conservation of original lattice momentum, it will turn out to be conservation of this little momentum. That's
So
all.
it's like there is a delta function over which you have integrated.
Yes, I've integrated out the delta function and kept 3 independent variables. So basically the correct way to rephrase what you said, this 4 is not independent number. If you tell me 1, 2, and 3, I know this guy's omega and I know this guy's little k. So we want to add this thing, and now we want to see what it does when I reduce my bandwidth from lambda to lambda over s. So remember, this is a shorthand for many integrals, right? There's a d omega 1 from minus, d omega from minus infinity to infinity, and a dk from minus lambda to plus lambda. For every one of them. There are 3 omegas and 3 k's looking like this. Now if you want to eliminate all the variables from lambda over s to lambda, it is not so simple here. Maybe someone can tell me why it is not so simple now. Eliminate them. Any proposals on why it's harder now? Somebody's got to know this.
Because it's an
Yeah.
interaction, so it will, if they are not independent, different k variables are not independent.
It's the different psi variables that are independent. In other words, what I have upstairs looks like a psi bar, psi, right? And every psi has got a psi bar low frequency plus psi bar high frequency. High momentum. There are 4 such things. So when I open up the bracket, there are going to be 16 terms. I want to keep anything that says low. Low meaning between 0 and lambda over s, and high is between lambda over s and lambda. You can always divide the psi in expanded momentum states as the part that involves low momentum and the high momentum. If I open up this is a compact notation, integrated over all these k's, hides the fact every dk has a part inside when you cut off and outside when you cut off. So I can decompose the field that way. There are 2 to the 4 terms. The part that's completely low will pick a low from here, low from here, low from here, low from there. But there are cross terms, maybe 2 lows and 2 highs. So when I integrate the high, these lows will be standing there. They're like the x squared, y squared term from the other day, and you've got to keep track of them. That's what makes it hard. But I told you the other day, yes.
Is there any special difficulties for the fact that fermions or
The usual.
bosons were easier?
No, fermions are a constant source of pain in the form of minus signs. But there is nothing else. You have the Wick's theorem for this. You can bring it down, you can expand it, you can find a correlation. Every time you flip the order, you've got to keep track of a minus sign. That's it. If we were not made of fermions, I'm sure we would not go near them. But you and I are primarily fermions, so that's not a big price to pay for being here. Okay. All right, so you see the problem. This is like the x, and this is like the y. This is like x plus y to the 4th power. Then there is one term, which is x to the 4th, which I said is called the tree level. And that's what you get for free, because that you can pull out of this. It doesn't involve the ones you're integrating. So let's just look at tree level. In the tree level, what you get is to simply say, I'm going to ignore the variables I'm not interested in. And all of these will now become the low energy modes. That's one term like that, which is sitting outside of everything. Then there are cross terms. For the term that's sitting outside, the tree level gives me psi bar, psi, u, d omega, dk. I'm writing the compact notation. All I want you to know this is that now these guys live in this region. You agree? All the omegas are present, but the k values are now limited to this new range. So upon mode elimination, approximately, not exactly, where I just keep the terms involving only the low part of every one of those terms, analog of the x to the 4th term. This is not yet my RG. Because my RG consists of mode elimination, followed by rescaling of momentum, followed by rescaling of the field. So if I now write this, there are 3 omegas and 3 k's. If I write them in terms of the new frequencies, I will get S cubed here and S cubed here. And these fields, when I write them in terms of the new field, psi prime, remember each one gets an S to the 3 over 2, so you will get another S to the 6 from the top, so this will cancel. This U would have become U of K prime over S, omega prime over S. The cutoff will now be minus lambda to lambda. Because if you do the rescaling, the cutoff will come back to the old value. And the powers of S you get from rewriting omega and K in terms of the new omega and K are precisely cancelled by the ratio of the fields. See, every S to the minus 1/2 can be absorbed to find a new field. So what do I have in the end? I have a theory with the same cutoff as in the kinetic term. Then I have 4 fermion fields normalized just like in the kinetic term. And this guy sitting here is the old U at K prime over S and omega prime over S. You agree, this is what I should identify as the new U at omega prime K prime. This is what I would call the new interaction, because the new interaction multiplies the new fields integrated over the new omegas and new k's over this bandwidth in the new problem. So what I want to carry from all of this is that I have found a way to calculate at tree level the following result: U prime of K prime and omega prime is equal to U at K prime over S and omega prime over S. That's the result of this calculation. Now, this doesn't look like your standard renormalization of a coupling, but it does tell you. See, the point is, we are always used to thinking of coupling constants. In field theory, you put one number in front of the 4 Fermi interaction, maybe a number U naught, and you call that your interaction. That's not the most general interaction. Interaction can depend not only on the labels of the external fields, right and left. It can depend on the frequency, and it can depend on the momentum. We are accustomed a lot in field theory to taking couplings that don't depend on omega and don't depend on K. In general, they do. Therefore, in the new world, with the new cutoff, at every K prime omega prime, there's a new interaction related to the old one in this fashion. But if you like coupling constants, here is what you can do. Let me lump K prime and omega prime into a single quantity called Q prime, because I'm just tired of carrying them, and they scale the same way. The claim is U prime of Q prime is equal to U of Q over S. This is the whole function. Now, let's take the function and expand it in a powered series. On the left-hand side, I will have the 0th order coefficient, U1 times Q prime plus U2 times Q prime squared, etc. To do a Taylor expansion around the origin, this function, and do the Taylor expansion on the right-hand side, you'll get U0 plus U1 times Q over S. I'm sorry, this should be prime, Q prime over S, plus U2 times Q prime over S squared, and you compare it.
That's actually prime.
Where?
U0 prime, U1 prime.
Yes, I'm sorry. These should be called primes. They are the expansion of the prime function in its Taylor series. In other words, this is not the renormalization of one or two numbers. It's the renormalization of a whole function of all these momentum. But if you want to keep them manageable, imagine expanding them in a Taylor series and keeping track of the Taylor coefficients. Each one is like a coupling constant in this theory. So now compare the two sides. You find that U0 prime is the same as U0. U1 prime is U1 divided by S. U2 prime is U2 divided by S squared. So this tells you that the higher terms in the Taylor series are irrelevant. They are going away. So even though they were present in the beginning, by the time you come down to very low energies, that means lambda goes to lambda over S, where S is very large, these couplings all die out. That means the omega dependence and the k dependence of the coupling constants are not important. You should ask yourself, what will I get if I kept this term? If this was an omega, q can be omega or k. If it's an omega, it means there are time derivatives of the fermion fields, or space derivatives of the fermion fields. But what you're learning is the only interaction you need to keep involved is the product of the Fermi fields in real time and space with no derivatives. So for Fermi does not have to mean no derivatives of frequency space. If you put an omega here, it's like take the derivative of these in time. So we're learning those couplings that are relevant. So we've already made a lot of progress. The only interaction that can possibly be of any importance in low energy physics is this guy here, U0. Not only that, somebody can say, well, what if I put 6 fermions? Psi bar, psi bar, psi bar, psi with some function W. There you can show, by same argument, even W0 is irrelevant. So forget about 6 fermion interactions. These are things you may or may not know, but this is what the theory is telling us without, just by applying the RG, you can tell what interactions are important for low energy physics. So we're down to U0. So everybody is out. So let's look at U0.
Question.
Yeah?
Does this answer change if we include more than 3 levels? If we go
Yeah, it could change. But you will find out that if you go beyond 3 levels, you'll be doing a perturbation expansion in U. So if something is irrelevant by 1 power of s, perturbation will change the 1 to 1 minus and U0 squared. If U0 is small, something irrelevant by an integer power of s cannot be restored to. But something like this does happen in the theory. I'll mention it near the end. But for weak coupling, this won't happen. So you might say there's only one coupling left, but remember, you got to be a little careful. The one coupling, U0, could be a function of its left and right labels. For every choice of these labels, that's a coupling. There are apparently 16 couplings. You can pick these any way you like. Turns out there's only one independent coupling in this theory, even though there seems to be many. Because if you now consider an interaction, this could be left or right, this could be left or right, that could be left or right, that could be left or right, and that's the corresponding U. First, I will tell you that you cannot have both guys coming from the right or both guys coming from the left. Incoming lines have to be from opposite sides of the Fermi surface. Because if they're from the same side, you will have an interaction that looks like, say, psi bar left, let's say psi bar left, psi bar left. Let's take a process where left scatters onto left. This guy is going to be 0. Why? Because it's multiplied by some U, left. Then you got the dk1, dk2, dk3, d omega 1, d omega 2, d omega 3. But if you took any function here, let me rearrange it so that the bars are there and the non-bars are here. Psi bar. This psi bar left is a function of, say, k1 omega 1. This is psi left of k2 omega 2. You can exchange these two and get a minus sign because these are Fermi fields. Then you can relabel 1 as 2 and 2 as 1. That won't affect anything. The answer will become minus of itself. That means it is 0. Now, if this had some k dependence, that's not true anymore. For example, if U, instead of being a constant, it will look like k1 minus k2 times k3 minus k4. Then if you exchange 1 and 2, this will pick up a minus sign. That will compensate this minus sign. That interaction is allowed. But we have seen k dependence of the coupling is irrelevant. So the things that you can keep are incapable of picking up an extra minus sign. That's why you cannot have scattering from the left. 2 incoming particles from the left or from the right. There is no such term in the Hamiltonian. So the only thing left can be left going into right. Then if you exchange 2 of these lines, you can show you just get minus of that interaction. So consequently, there is only one U. All the other U's are the same up to a sign. I'm going to call that one U0 to be, say, the left, right. This is what we can learn from the tree-level calculation. Tree-level has told me no 6 Fermi interaction, no 8 Fermi interaction, only 4 Fermi interactions, and that too only with a constant interaction, no omega, no k dependence of the coupling constant. But at the tree level, that coupling is marginal. You notice U0 prime is the same as U0. It's not getting big and it's not getting small. So what do? We got to go and do the thing we don't like to do, which is to do the next order in the calculation. For which I told you there's a way to do diagrammatic corrections. Now I have to assume that you are familiar with Feynman diagrams to tell you what the diagrammatic corrections are. And another way to think about diagrammatic corrections. Suppose you're doing a scattering amplitude of 4 fermions. That answer is called. Let's call the whole thing as some function u. That is equal to a u0 you get from your Boltzmann weight. Then you're supposed to draw a diagram that look like this. Let's say this is left, this is right, this is left, this is right. Then you're supposed to add this diagram. Left, right, right, left, and you're supposed to add this diagram. Left, right, left, right. And at every corner you put a u0. I'm not doing RG now. Suppose you're doing straightforward perturbation theory. In a theory of the cutoff, that's a whole bunch of diagrams, which you sum them all up, they will tell you what's inside the black box. That's the real scattering amplitude for 4 fermions. Every integral will go from minus lambda to lambda in the loop momentum. And this is the coupling constant that you put in. Now, somebody comes along and says, I want to use a smaller cutoff. I want you to cut off lambda over s. So he will use some u0 prime. I shouldn't call it prime. This is u0 for lambda. This is u0 for lambda over s. We'll draw the same diagram. Let's just draw one diagram. It's enough to illustrate what I'm saying. Here the momenta will go from minus lambda over s to plus lambda over s. Now how can these two people get the same answer? You got to think. When you change the cutoff, you want to get the same answer as before. What do you have to do? Well, this guy's integrals are going over a smaller range of momentum. There's something missing here. What's missing here is the momentum between lambda over s and lambda. That's what this person would have. So what you do is you shift those missing terms into this. And you say the u0 for lambda over s should be the u0 for lambda plus a diagram like this and 2 other diagrams, but these momenta go from lambda over s to lambda. They live in the region you've eliminated. Yes?
Let me ask a question. They would throw out something like forward scatter. Like, for example, you throw out something like psi bar left.
Psi left.
Psi left.
I mean psi left, psi bar left,
Yeah.
yes.
So that term, if you think about density of those things,
Yeah.
that term can be renormalized from the velocity. Right? Because it's a row left, row left.
It's row left, that's right.
Right. So the kinetic energy can write as row left, plus
Yeah.
row right, row right. So if I have an extra term like that, wouldn't that change my...
No, I don't think. I have to think more carefully, but that term will simply vanish here. It's not going to be allowed.
Yeah, here, but I wonder if it's because it's sort of when you go from...
Well, you may have done that in some Hubbard model, where you have spin. If you got spin, it's possible to keep such a term. But if you have no spin, I'm pretty sure that is no such term. I'll try to... Look, if I'm wrong, I'll come back and announce it. We'll talk about it after the break. Yes?
This argument about the fact that U is only constant has to break down for long-range directions, I suppose.
Ah, very good. Let's ask this question. What about long-range interactions? If you have long-range interaction, it means the coupling constant U does not have a Taylor expansion at the origin. So this whole thing assumes that incoming interactions are short range. Once you're done with that, Mr. Wilson assures you that the renormalized interactions will also be analytic, because in going from one to the other, I'm integrating over momenta, which I emphasized many times. Like I have a lower cutoff and an upper cutoff, completely analytic. The long-range interaction, you cannot do the usual argument, you've got to be careful. That's also why I'm not a fan of some people who integrate out all the low energy momenta of one species of particles and get an action which is non-analytic to begin with for the remaining variables. Then you cannot do this thing. The whole power of Wilson's method is there is no non-analyticities encountered anywhere except the ones you put in by hand. Yeah.
Also, this argument holds necessarily for any theory with certain interactions. Then dimensionality.
Well, I don't know about any dimensionality, because in one dimension I had two Fermi points and I did this. In high dimension you got to think about what you have to do.
But you go down to directions or not?
Yeah, you'll have to do it again in higher dimensions. I did it specifically for one problem in one dimension, just to show you what the RG will tell you. RG tells you that the interaction you put in is marginal. It means it could be dangerous, because we don't know yet whether it's growing or not growing. If it was simply irrelevant, you can go home and say there'll be region of stability of the gapless metallic phase. But we don't know if this coupling is going to go up or down. It hasn't made up its mind. So we want to see to next order whether it will increase or decrease. But I'm telling you, by this argument, that the coupling of the new cutoff is the old coupling plus parts of the loop diagrams that are missing. So let's calculate one of these diagrams. We really have to add two more terms. So d u0 of the one non-zero coupling has three parts in it. So I'm going to write those three parts. These factors of half and so on, you have to do some work to get them. So this is left, right, left, right. Okay, now, it's not enough to say left, because I remind you, here's what we're working with. Here is my minus kf, and here is my plus kf. I'm going to eliminate now an infinitesimal region. Now I'm going to do something slightly different. I'm not going to eliminate from lambda over s to lambda. I'm going to eliminate from lambda to lambda minus d lambda, so that I can get a differential flow. So the variables I'm eliminating lie in a very thin slice, d lambda. So look what happens here. In the left side, when I have a fermion, you can ask, where is it on the left Fermi point? If it's near this cutoff, is it there, or is it here, is it there, or is it here, where is it on the left? It doesn't matter where it is, because u0 does not depend on k or omega. Therefore, we can pick for all of these states 0, 0 for k and omega. You just have to say whether you're left or right, but the external variables can be kept equal to 0 if the coupling doesn't depend on the external momentum or frequency. So you choose them to be 0, that makes life easy. You can pick them to be non-zero, make your life hard, but that's the more difficult way to find the flow of u0. So every external omega and k are 0. Therefore, if this loop momentum is some k omega, that's also k omega, because there's nothing on the left-hand side, no momentum transfer or frequency transfer. Here, if this is k omega, I claim this is k plus pi omega. Why is that? Because when the left scatters to a right, the difference between these 2 points is pi. You have momentum transfer pi. There's no frequency transfer because nobody got any frequency coming or going. So this line and that line look like that. And look here. Left and right have 0 total momentum and 0 total frequency. So this guy is k omega. This must be minus k minus omega. This big K is the real lattice momentum rather than measured from any Fermi point. It's convenient to think in terms of that. You've got to do these three integrals, and these momenta have to lie in a shell of width d lambda. The shell can be this one, this one, this one, or that one. That's what you have to eliminate. Taking the cutoff, making it a little smaller, there is a positive momentum of cutoff lambda, you got to cut that down. There is something at minus lambda, you got to bring that out here. Then on the other Fermi point, there are 4 regions you want to eliminate. So this guy can lie in any of those 4. So look at the first diagram. There are some u-naughts everywhere. But forget the u-naught. Look at the variable you're integrating. It will look like some loop integral, d omega dk divided by I omega minus d of k, and I omega minus d of k. With the same k, that's the main point. Now, if you know any complex variables at all, you will realize this integral is 0. Because it's convergent integral, but the poles lie at omega equal to minus IE and omega equal to minus IE. Both the poles are the same half plane. So that means you can close the contour the other way and get 0. That happens in all these theories, that if you got propagated the same k and omega, they will not contribute. So this diagram doesn't contribute. Then I come to the second diagram. I don't want to write the whole thing down, but let's think about this. What about the second diagram? This has got k, and that's got k plus pi. You remember the energy formula was cosine k. So when you add pi to that, you change the sign. So E of k plus pi would be that. But now the poles lie on opposite sides. So you cannot get out of it. When one pole is here and one pole is here, no matter how you close it, you'll get an answer. But let me write down the answer, and I think you guys can believe that. This looks roughly like omega squared plus e squared. And that, I claim, will look like dk. The k is at lambda. When you do the integral, when you do the omega integral of d omega over omega squared plus e squared, you will get 1 over mod e. And dk is a sliver of science d lambda, and k is at the cutoff, so you get d lambda over lambda. The factors of pi and u, which I will just tell you what they are, is u0 squared over 2 pi. u0 squared is obvious from here and here. That's the contribution from this diagram. So it tells you du0 is this. It's common to call d lambda over lambda as a variable dt. That tells you du0 dt is equal to u0 squared over 2 pi. This tells you that as you go on eliminating variables, u0 will grow. It starts at small value, it will get bigger and bigger. But of course, this is not the whole story. I have to look at this diagram. When you look at this diagram, let's try to do it again. This is something probably going faster than you would like, but I don't have time. You'll have to fill in the blank later if you really want to know the detail. Here, one guy is at k and one is at omega, other is at minus k and other is at minus omega. Now I will use the fact that E of minus k is the same as E of k, but of course I will put the minus sign in front of the omega. Then again, the poles are on opposite sides, and you can do this integral. And amazingly, that contributes minus u0 squared over 2 pi. So you notice then, in this theory, there is one diagram that gives a logarithmic derivative of the flow of the coupling, because d log, this is just d log lambda. That means if you really drew this diagram, it'll have a cutoff dependent that goes like u0 squared log lambda, and if you took the d by d log lambda, you get u0 squared. It is a logarithm that leads to infinite response to charge density wave formation. Similarly, there's a logarithm in this diagram, otherwise you wouldn't have gotten this du d log lambda. That's why the system likes to be superconducting. So if you only focus on one or the other instability, you can get immediately it becomes superconducting or immediately CDW. But what this tells you is, as far as the coupling is concerned, the two terms cancel. And u0 doesn't flow at all to one loop. And it's interesting that if you do this 37 loops, you will find u0 doesn't flow. That's something you have to prove by some other methods. And we also, turns out that problem can be solved exactly So we know what happens. So this is a rather unfortunate example because it introduces you to a complication that's very rare, which is that for every value of u0 up to some value, the coupling is truly marginal. And at every value of u0, you have a different fixed point theory. And each fixed point theory will have its own power law behavior of all the correlation functions. And they depend on the value of u0. Now you can ask yourself one question. If this thing is called the beta function. Beta function is the response of the coupling constant to change the cutoff. It is strictly 0 to all orders in this perturbation theory of this time. How does it ever happen that beyond some point, suddenly some coupling grows? Well, it turns out the thing that grows is not this coupling. This coupling is completely frozen. There's another coupling, which I ignored, which will suddenly become important. That's the coupling where you have left going to right. Now, can you ever go left to right? Can you have two particles from here going to two particles there? Yes, because the violation of momentum is 2 pi, and 2 pi doesn't come on the lattice. That's allowed, but then Claudia will say, you just convinced me the left vanishes. That vanishes because you have a psi left of some k1 and the psi left of some k2. And I said exchange 1 and 2 and you get a minus sign. And the coupling constant is not able to do anything. But there are corrections to the coupling constant that look like k1 minus k2 times k3 minus k4. So that if you exchange 1 and 2, these two will exchange and you will not be 0 due to the Pauli principle. But when you do the RG and you rescale the coupling, because of the extra power of k, when you write that in terms of new momentum, you will get a 1 over s from this and a 1 over s from this. You will conclude that coupling is irrelevant. So that coupling is actually irrelevant with respect to this fixed point at the origin. What I'm showing you is that if you move here, that's also a fixed point. Not obvious, but you find by doing the flow that it's not flowing. These are all different fixed points. So at each fixed point, you've got to ask yourself, is that interaction relevant or irrelevant? And the status changes from being highly irrelevant by 2 powers till it becomes marginal and then relevant at that point. So it's this coupling called the Umklapp scattering, where there's violation of momentum by 2 pi that becomes relevant beyond this point. And that's what leads in the end to charge density formation. So this is the long and detailed story of RG in 1 plus 1D. I mention it because it exemplifies how you're supposed to use the RG. It tells you that it is not prejudiced about either PCS instability or charge interior instability. It tells you if the two fight each other out and cancel, it tells you they cancel. It gives you the final fate of the theory. If some term had been absent, so that it was like this, then you can conclude that if this term had been absent, second term, you will conclude u0 is a relevant parameter and it's going to grow. It's going to grow more and more and more. Then you can ask yourself, in that case, let me focus on the u0 term of the Hamiltonian and see what it likes. We can show that if you give an average value to the density that alternates, then the u0 term will have negative energy. That's how we will guess the answer. Suppose this term was absent, but the second term is present. That means du0 dt is minus u0 squared over 2 pi. That means if u0 is positive, it will flow to 0. But if u0 is negative, it will get more and more repulsive. That means if you had an attractive interaction, it will become magnified by the PCS instability. If you had a repulsive interaction, it will get amplified to form the charge density wave. But this theory turns out for either sign of interaction doesn't leave the starting point because these two effects cancel. And this is called the left interliquid. Everybody dreams about getting it in higher dimensions, but not with any success. As you can see, it took quite a miracle to have one flow precisely cancelled by another flow. And one set of diagrams want you to go one way, other wants you to go another way. The chance that they will all cancel exactly in higher dimensions is very improbable, and I have not seen a good example yet. But this was a dream for a long time to find this kind of behavior in higher dimensions. Alright, so I'm going to lay the groundwork for life in 2D. I want to stop and ask if you have any questions now. I'm assuming you will ask them as they arise. Okay, so now I want to, my goal of course is to go to higher dimensions. I mean, yeah. Any question?
So, following that, now that you have this K1 minus K2, K3 minus K4, what happens to the forward scattering?
Yeah, it can be non-zero. Not for between left, left and right, right.
Yeah.
Yeah, that interaction is non-zero in the region of strong interaction.
And what about left, left, going to left, left?
Yeah, that's still there. Nothing is forbidden now.
Yeah,
Or left.
is that relevant? Once this guy becomes relevant?
Well, you got to see. I have to think about, I know the umlaut operator becomes marginal and then relevant.
Sure.
I have to think about the left, left going to left, left, what it does. Yeah? Yes?
I have a question. One of the things that's essential about one dimension is it has a lot of special conservation rules.
Mhm.
And in particular, one can show that the low energy spin and charge have been decoupled from one another. Does that play a very important role in what we've just done? Is that the reason why you can't generalize the higher dimensions?
Well, my example doesn't prove that because I did not include spin at all. But if I included spin, you will see what Pierce was saying. That in this theory, charge and spin have a way of behaving independently. Of course, one dimension is very, very special. That's the key to all of this. The most important property of one dimension is there are only two Fermi points. And each Fermi point describes one species of relativistic fermion. It looks like standard quantum field theory. And this renormalization I did, you can read out of any textbook for standard field theory. The really new aspects are going to come when I go to higher dimensions. Yes? Yeah?
So, if you have a theory like this and you find, you start by looking at a Gaussian theory and you have a fixed point there.
Right.
And then you find that one of the interactions you added is actually relevant.
Right.
Then at the beginning it seemed like you chose the free theory fixed point specially and then scaled around that so that term was invariant.
Right.
Would you have to do anything to change that if you found that in fact the theory was going to run off to some other?
Well, yes. If it runs off somewhere, your job is to find where it stops. And you have to guess where it stops, let's say. But even if you guessed it right, it's very hard to prove that you're right. Because the new point is an interacting field theory. You have to find the perturbations with respect to an H0, which is an interacting H0. That means the Green's functions are that are not known. Here the Green's functions are the correlators are all simple 1 over omega minus something. That's why it's hard to verify the stability or the existence of non-trivial fixed points. And for that, people use what's called the epsilon expansion, where if you come slightly below 4 dimensions, you can find the presence of non-trivial fixed points, where U0 is not 0, but of order epsilon. And you can use the smallness of that to demonstrate order by order and epsilon that you have a fixed point. Yeah, to show you have non-trivial fixed points is very difficult. That's why people looking for non-Fermi liquids in 2D and so on have had difficulty. Because first of all, you've got to guess what it is doing at the fixed point. Then you've got to prove it's a fixed point. That's very hard. Yes?
The starting point of this calculation is to linearize the spectrum.
Yes.
So which gives you very similar result to personalization technique.
Yeah.
So can you take into account the non-linear dispersion?
Yeah, you can. I mean, if I put a k-squared term in my kinetic energy, it'll have a term that looks like I omega minus k squared. And I will write everything as that over s, that over s, that over s squared. This s will go away in redefining the field. The one s will be left over. And I will conclude this is irrelevant. Okay, I want to start by just saying a few words about higher dimensions, because that's what's the motivation for this whole work. Everything I said till now was sort of known at the time. But the big question when I got into the field was, in 2 dimensions, can you get something that's very different from the standard liquid called the Fermi liquid? So my view was, look, I don't know what can happen, but I will use the RG because it's a very reliable way to see what will happen. So let's take now fermion in 2D, not on the lattice, in the continuum. The Hamiltonian for the non-interacting fermion is just k squared over 2f. Now, you know, if you took this Hamiltonian in second quantization, it looked like psi dagger k, psi k squared over 2n. Again, I have no spin. Ground state of this Hamiltonian is no fermions, no energy, nothing. It's not very interesting. You want to have some number of fermions, then you got to modify the Hamiltonian by a chemical potential, so that for small values of k, the energy is negative and you occupy it. So you will occupy all states up to k squared over 2m equal to mu. That means you fill a Fermi C. This is your filled Fermi C, and that's the analog of this guy. But now what is the low energy physics for this problem? Low energy physics, again, is regions near the Fermi surface, not near the origin. So what I want then, I start with a theory in which I have a bandwidth of lambda above and lambda below the Fermi momentum. That's it. The two Fermi points with the bandwidth now become a ring with an annulus around it. That's my low energy region. And if I take k squared minus mu, I can write it as kf plus some little k squared over 2m. Mu can be written as kf squared over 2m. If you imagine opening this out, you will find the kf squared over 2m cancels. That's the term linear in k that I will write as bf times k. That's the term quadratic in k, which I will ignore for the usual reasons that it's irrelevant. So this whole Hamiltonian then will contain, when you're finished with everything, just some bf times k, where k is k minus kf. So what's the action for the non-interacting problem? Well, I've done all the warm-up, which is why I wanted to do this part today. How is this guy different from what I did in 1D? In 1D, you had a range of k in the radial direction and two Fermi points. Now I have a range of k in the radial direction from minus lambda to lambda, but the whole angle full of Fermi points. Therefore, the Hamiltonian here looks like dk d theta psi dagger of k and theta times bf times k times psi of k and theta. This is the Hamiltonian, not the action. Instead of a sum over alpha, I'm an integral over theta. That's it. No other difference. So the non-interacting action will look like d theta, dk, d omega, theta from 0 to 2 pi, k from minus lambda to lambda, omega from plus to minus infinity, then psi bar of omega, k, and theta instead of subscript alpha. And I got I omega minus k times psi of omega, k, theta. That's the non-interacting Hamiltonian. Just like 1D. This is one interesting thing you notice. Even if you go to 96 million dimensions, what will you have? One huge sphere, right, of 96 million minus one dimension. There will be a radial direction in which you will have an energy cost, and the rest of them will be like some internal labor on which nothing depends. Theta will be angle on this huge n minus one dimensional sphere. So 3D, 4D all look like one dimensions, because all the angles behave like internal labels on which nothing depends. The energy depends only on the radial one. Okay, so this is the first thing. The non-interacting fermion 2D is given by this action. How about the fixed point of this? I don't have to repeat it, which is why I wanted to do that today. Do the same thing. Change lambda to lambda over s. Change the momentum, change the field, rescale everything. What will you get? You will get the same action back, provided psi prime of k prime, omega prime, and theta is psi of k prime over s, omega prime over s, theta divided by s to the 3 over 2. Absolutely no difference. Everything is the same because you replace an internal label which has two values by an internal label which is an angle. So then if you continue and say what happens to the coupling constant, the coupling constant u, which can depend on all the possible k's, all the possible omegas, all the possible thetas, will not depend on k, will not depend on omega, just like before, at free level. So u is a function of this theta 1, theta 2, theta 3, and theta 4. That's like depending on left, right, depends on these 4 angles. So at the tree level, there is a coupling function of these 4 angles. We got to decide what happens to that coupling function when I do the loop corrections, because the tree level is not able to render unambiguous verdict on this coupling. It's not going up or going down. Maybe what you saw in 1D will happen. Maybe it will be marginal, maybe it will be relevant, maybe it will be irrelevant. We have to find out. But you've already learned, this is the whole point. When you go to 2 dimensions, low energy theory is described by a function of these angles, not function of the radial momentum, not function of frequency. We will come back next time, tomorrow, and find the fate of this thing. What we find is, out comes from this, the theory called lambda permealiquid theory, with all its known possibilities. All right, I think this is a good time for me to stop talking. If you've got questions, I will answer them as long as audio permits that.
I think that for a while. Okay, any questions? I have one.
Yes.
So when you said that if you just look at the coupling that's growing, you can tell the stability, you can tell what the system does.
Right.
But it's not that obvious that you can always do that. So for example, in some cases when you go to some short density wave or a conducting channel that coupling constant is growing, you can tell. But let me give an example where things get more confusing. If you add disorder, if I had a quench disorder with the integrator over disorder, I'll get an effective four-fermion interaction, which actually have one less power of momentum because of the quench or
Yes.
time, frequency. Therefore, that coupling would be relevant in any dimension. So that would tell us that, okay, disorder is relevant, so it's growing. But if you naively just think, okay, disorder is growing, you'll say, well, it's going to get very large, and then disorder is very large. And then the quantity would localize ourselves. But in reality, what's happened is that disorder is growing. So it says that your fixed point, starting fixed point, which had plane waves, which had your basically I omega minus k, that's
no good.
That's no good because the wave functions are going to be superpositions of many of them because of the scattering. So that kills that gives the quasi-particles in the original fixed point some lifetime. But that doesn't mean that you have zero conductivity that all states are localized just because that coupling grew. So you actually have to go and look at another density mode, and then depending on dimensionality, the disorder, you may still have a metallic system. So that's one example where just seeing the flow doesn't tell you exactly what's going on.
Well, the flow will tell you that you're screwed. Now, what happens to you next is your problem. If the coupling vanishes, then you can go home to your wonderful fixed point. If it grows, you know you've got to deal with a novel physics, because what does this new term like to do? Sometimes it's a very simple term where you can tell it likes to have a contradictory wave, it likes to have a padding instability. It's quite possible I write some term in Hamiltonian and I say this term is large. What does it like to do? Maybe you're saying you cannot guess the new ground state that this one would prefer.
You can guess, but it's an educated guess. Like in the case of superconductivity and CW, we know that we have a leading solution that tells us roughly what it is, but if we're educated in what it is, then
right. I think the real progress is not when you find a coupling is relevant, then of course it's going somewhere. You can often find, if you take in more terms, the flow will go somewhere else and stop there. Then you've got a new theory, and you can really try to ask, what is the nature of the correlation functions at the new fixed point? If you, by some trick, you can bring the second fixed point very near the first fixed point, you can analyze it in perturbation theory. That requires introducing clever ideas like varying the number of dimensions from 3 to 4 minus epsilon and playing with the epsilon, or from 2 to 2 plus epsilon. You need some trick to find the fixed point and to work with it. Yes?
So, from your calculation, you show that below certain value of U, you have a whole bunch, you have a whole line of
fixed points.
Is this the origin of in the Nottingham liquid? You have the power law,
yes,
which
exactly
is
correct.
The U.
Yes.
So from your calculation, you show that when U is large enough, you break the
Yes.
liquid
Because what happens in the Lagrangian liquid is at every point in the Lagrangian liquid, the relevance and irrelevance of various operators is constantly changing. And suddenly one guy who was initially irrelevant becomes marginal and then relevant. And that will make you do something. So something, of course, has to be this charge density ordering, which you can figure out very early. Today I showed you that U is very, very large. You know what it likes to do. Full empty, full empty. You will go into that state. Yes.
Any more questions?
One question. Sorry, one thing that I missed before and then I forgot to ask. You use three-level arguments to show that there is no dependence on K or omega.
Right.
And then from that it follows that the left level that term vanishes,
Yeah.
everything, and you have actually one couple constant.
Right.
Then later on you say you move along that line, you're not marginal, but your theory changes. And then left to right, for example, the unflat term becomes allowed.
Yes.
I missed why.
Why is it allowed?
Yeah.
Because the way you do the scaling, why did you decide it's unimportant? You took the non-interacting fixed point and scaled omega and k in a certain way and concluded if you did that, this coupling will be the starting value divided by s squared, for example. But that was the physics at this fixed point. If you go to this fixed point and that fixed point, you will find in the RG, when you do mode elimination, omega and k are going to be scaled by some non-integer powers to make them fixed, to keep the fixed point fixed. Therefore, if the powers of omega and k are not omega prime is omega over s, but some new power law, then it's not clear that some operator that looked irrelevant will continue to be relevant. In other words, I did all my analysis at this fixed point, which is a free field trivial fixed point. If you go to a point here, it's not easy to figure out how to scale the operators to keep that point fixed. Omega and k will have to be scaled with non-traditional powers. K prime is k over s, and omega prime omega over s. It's called engineering dimension of omega and k, but you can get funny powers, and you do get funny powers. Therefore, the new operator, k1 minus k2 times u, how does that behave? It may have funny powers in it, so that in the end, there are no negative powers of s. And soon there will be positive powers of s. And that's when, that cannot be shown perturbatively. We know this theory by other methods like Bose-Essential. That's how we can answer that.
Sorry,
Yeah.
just in this part, sort of, I can follow it. I don't know why. My problem is sillier. Left to right. Before you said it was 0. It was forbidden.
Yeah, because if you took a constant u, that term in the action will integrate to 0 because of the minus signs coming from exchanging psi left with psi left.
Yes. When this not become valid?
If the coupling constant u that multiplies it, instead of being a constant, had k dependence and looked like k1 minus k2 times k3 minus k4, when you exchange the Fermi fields, you get a minus sign, but k1 minus k2 will also get a minus sign. So you can no longer argue that it's 0 by Pauli principle. But you will argue it's irrelevant because it's got unwanted powers of k. That argument will break down as you go to strong coupling, when the importance of the operator is different. So I want to close by saying one thing. When you come tomorrow, you must remember the following, because I won't repeat that. You have to remember that in 2D, you get exactly what I did in 1D, except for the fact that the discrete left-right index is replaced by an angle. The coupling constant you need is only 4 fermions. By the way, this is true in, again, 96 dimensions. Fermions in 96 dimensions will only have a 4 Fermi coupling independent of frequency and wave vector. It will depend on the angles on that big sphere. No 6 Fermi, 8 Fermi for the same reason. So I will start at this point and analyze the fate of this U.
If there are no more questions, Elisa has some announcements, but before that, let's thank Shankar.
Just like that. So there is some news for you. I don't know if everybody is going to be happy. But first of all, there is a request not to drink and eat in this home. So there was some problem yesterday. We leave the door open to make it more fresh for you, but please don't eat and drink in this home. The second point is to clarify you about the poster presentation. So Pierce wants that everyone come here and give a 1.5 minute speech about his poster before we go to the poster session. If you don't, you have not sent your poster, it's not in the booklet, you should go and look for Bruno at the desk and give him the title of your poster, and even if you have the file, you can give him, and maybe we are going to make a final version of this to keep, and then your poster is going to be in. We need to know that because we should divide the time between the poster presentation. So everybody should be prepared to come here. We are going to do it in alphabetic order in the first name. Okay? And now some people that have not given the boarding card from their flight, the people we have paid from Brazil, they should bring it at the desk. Okay? And so now I'd like to talk about some amenities. We are planning tonight some, let's say, to go to a local where there is Brazilian music. It's downtown, it's a very nice place, and very safe, and big, and you can spread out or you can stay together. And this place works that you pay at the entrance something between, I don't know, $7, $8, and then you pay what you eat or drink at when you leave. So that will be by each one. And we should see that because we need to make a reservation, and I don't know how it works depending on the time that the poster session will be ending. But I assume that at the poster session you are going ahead to drink and eat something, then if you go there, you will only go for the music. About the excursion. So what we have planned is the bus will come and pick people here. We are going to prepare a lunch box, so you don't need to hunt for lunch before to go out to leave for the excursion, and then you can eat on the way and drink. And the plan is to go near to the beach, a bit more to Ipanema, and then to the lake, and then to the Corcovado. Then you should get out of the bus, take a train that goes through the forest to the Corcovado. Then you come back and you go to see Maracanã, downtown, and then you go to the dinner place. The dinner place is one of the best barbecue house in Rio that stays near to the bay. You know, so the Brazilians from Rio that are not invited for the excursion because they know all this place, they can go directly. And when you come there, there will be some drinks before till everybody comes, then we go, and be careful not to eat too much because it's completely free. For Thursday, there is another possibility for the evening. It's a place that's called City of Samba, and only it's open on Thursday evening. I think you should pay some, I don't know how much. The guy from the company will come, maybe $40 or something like that, but then you have drink and have beer, caipirinha, and something to eat, and you have a flavor what the carnival in Rio is, because it's the place where all this school of samba prepare all the clothes.